Sorry?
What better way to arrive in Israel?
I can start speaking in Korean probably. Okay, we are in class on statistical mechanics. The best grade, the best grade. I'm going to take the best grade out of the two. Mechanics. Okay, we found that the probability of a system to be in a specific state I with energy EI is e to the minus beta EI. Beta is 1 over k Boltzmann T. Okay, divided by z, where z is the partition function, which is a sum over all the states of the system, e to the minus beta EI. Okay, very nice. And how we connect it to thermodynamical quantities, macroscopical and not microscopical. So the Helmholtz free energy was minus 1 over beta log of z. Okay, very nice. Now, if we want to compute specific macroscopical quantities, or either we use some specific differentiation rules over the free energy, or we do it by the use of definition. So, for example, if we want the average energy, it is a sum of I, EI, multiplied by Fi. Okay. Now, in order to solve any problem with this canonical ensemble, we need two conditions to be satisfied. Right? One is additivity of energy. The second is factorization. The additivity of energy means that I can look at my system. I have to invent some particles that describe the system. It can be actual particles, right, like in a gas, or we will see in examples it can be something else. But we have to describe the system in terms of particles, or we see later degrees of freedom. And the total energy, this is additivity of energy, the total energy is a sum over epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4 plus epsilon 5, okay, which are the energies of single particles. Energies of single quote-unquote particles. Okay. Factorization means that, well, when all those energies are independent, right? So the energy that can be to particle number 1 is completely independent of the energy that can be to the particle number 2, 3, and 4, 5, etc., etc. If there is an independence, we have shown that, and this is 2, right? 2 is that z is a multiplication over what? J goes over all the different particles that I have in my system, Zj. Whereas what is Zj? Zj is again this partition function, okay? Zj is a sum over e to the minus beta epsilon, call it j, and over all the different states is my system, or this particle. Okay? So what factorization means mathematically, and we have shown this mathematically, okay, is that I treat single particles as microscopical single particles as if they are macroscopical systems, right? We developed this formalism over here on the right hand side. We developed it for what? For big macroscopical system. There was a heat bath, there was a constant temperature, well, different conditions, right? Now, we then did perform some specific tricks and math, and we arrived to this mathematical description. What this mathematical description tells us, forget about the conditions, right? Look on each single particle. As long as they are independent, for me it can serve as a macroscopical system. And I treat the different energies of this particle as if It's the energies of the whole system that is composed of one single particle. And that's it. So this is what we are going to do for any problem from now on. And this is what done till today for any problem in statistical physics in equilibrium. Okay? We need to find a representation of a given system that condition number 1 will be satisfied and condition number 2 will be satisfied. Okay. Now, it does not mean that all the systems are ideal Gauss. No, it means that we need to find a representation, and sometimes the representation is very, very complex. Remember, you've studied in analytical mechanics. There is this Hamilton theorem that says any problem in mechanics can be transformed into a system of free particles or harmonic oscillators. How exactly to transform it? It's a very difficult task. So this is exactly what is done in statistical physics. We have a complex system, and eventually we will try to represent it by means of very simple, quote-unquote, particles. That's it. Now, we've already seen one example, the two-state system. And what we are going to do today, we're going to see two additional examples. Right? The first example is the polymer model. So polymer, we assume that it's composed out of monomers, right? So let's assume that I have a lot of monomers that I represent them by arrows, and those monomers are somehow connected to each other, right? And in reality, well, this polymer can be three-dimensional or two-dimensional, whatever, and it's a complex connection between different monomers. So this guy is a monomer. And it's composed of, so it's a single molecule or simple building block of a very long molecule that we call a polymer. Okay? So this is all of this guy. This is a polymer. Okay? So it's basically a string of different molecules somehow connected to each other, and those building blocks are exactly repeating themselves. There can be some specific angle, as I plotted over here, that describes the connection. But in general, it's a long strings of monomers or molecules. Right? Now, of course, the connections between the different monomers are complex. There is such things as persistence length. So, for example, if one monomer, okay, which is one building block, is a small molecule and it has a direction that points in this to this side, the next one cannot simply point to the other side. They're all connected, they're all correlated. Okay? So it's a complex system. Now, we want to understand a little bit the physics of long molecules. So we're going to simplify everything, and hopefully we will still learn something about this behavior of long molecules. Right? So this is how physics works. We look on a complex system in chemistry, in biology, in human behavior. We say, well, this is very, very nice, but I cannot solve it. Right? Maybe I can run a computer simulation, but I cannot solve it. But if I will simplify enough stuff in this representation, maybe I can understand something about the physics that is actually buried inside. Right? So we cannot be very specific, but we try to be very, very general. All right, so how we simplify this? So this is true, and this is a mimic. Okay, we mimic this system. How we mimic a system? Let's consider that we have a wall, and I say the following thing. I have a set of monomers that are connected somehow to each other. They're all of the same length. Okay? They're all of the same length. the left-hand side monomer, this guy, is somehow connected to the wall. Okay. The right-hand side, I pull it by string, okay, connected to a string, and I put a mass of mg over here. So let's assume that mg equals some specific tau. This is the tension that I'm trying to pull all this polymer downside. Okay, so the question is why here it's disordered and here I have this specific set of a wall, one specific monomer is connected to the wall, and then have a string, etc. So experimentally wise, what people do for DNA is also a polymer or monomer. So when I want to study the properties of this polymer or properties of DNA, those are actual experiments done nowadays. For example, in Bar Ilan, the group of Yuval Garini, who is already not here, but was here till a year ago. So if I have, for example, a slide, on top of it there is a DNA strand, okay? What can be done in an experiment, I can connect a bead to the strand, I can shine a laser light on top of this bead, capture it, this bead is actually in a force, which is called the optical tweezer, and start to pull this polymer. Okay? Right? So this is, in a free way, this polymer can be whatever. In an experiment that people actually doing, they're trying to do, well, they put a wall, they put this polymer inside, or DNA, and they try to pull it. How exactly they pull it? Well, it depends on the specific experiment. So this is what we are trying to mimic here. We have a polymer that we describe by those arrows, and we also try to pull it. Now, this is just a simple representation. In a second, you will see that it's actually not very correct. Okay. And I will explain why it's not very correct. Look, the idea is I cannot solve a given physical system. It's too complex. There is huge number of monomers inside. They are all correlated, extremely correlated, and it's impossible to solve it exactly. It may be possible to simulate on a very strong computer small portions of a DNA, okay? But it's impossible to simulate the whole behavior of the whole DNA. It's just too complex. Right? So eventually that leads us to some very simple models. So those are my building blocks. I'm looking at each building block and I'm asking the following, I'm saying the following thing. Each building block can be in one of four states. So this is a simplification. Here, each monomer can, be in any direction that it likes. I'm saying let's simplify it. We choose only four specific states for each monomer. Okay? So it can be either going to the right or to the left. Okay? Can be down or it can be up. Now, I know that when I pull the string, my monomer, all the polymers would prefer to go in what direction? In the direction which points to the right, right? Because I'm pulling from left to right, so the monomers will prefer to go or to follow the right direction. So I'm saying the following. So if the monomer is pointing right or is pointing left, okay, the energy in this state is 0. Okay. If the monomer is pointing upwards or downwards, there is additional cost of energy. Right? It's not pointing exactly in this bias that I'm imposing. Right? It's going in a perpendicular direction, so it has to cost some energy. Right? Has to cost some energy. Why I'm saying it has to cost some energy? Remember, the energy has to be what? Minimal. The energy has to be minimal, right? So when I'm trying, so what it means? The energy has to be minimal. When there is a preferred state, what is the preferred state? To lie in the direction of the force, right? I have like a magnetic field, and the particles want to lie in the magnetic field, right? So then those are the preferred states. Anything that is not in the preferred state has to have some additional energy, right? It don't want to be in this direction, and does not want to be in this direction. So I will attach to those unpreferred states an additional energy. Let's call it epsilon. Okay. Now, so this is first simplification, right? The first simplification was that my monomer here can point in any direction that I like, right? In a real situation here or on DNA. But in my model, I'm saying the polymer can point only in a very specific direction, which is x hat, y hat, minus x hat, and minus y hat. Right? That's just a second. So this is x hat, y hat, minus x hat, and minus y hat. Yes? Okay. So I cannot plot three-dimensional stuff. Okay. So first simplification is specific state. Second simplification. Remember, I have two conditions when I can solve something. What are the conditions? Additivity of energy, which is usually fine. The second is they are uncorrelated. Okay, so I'm looking on this and I'm saying, well, if this guy, this monomer, points to the right, I know that in real life system there is this angle theta between two monomers, and they are affecting each other. They somehow affecting each other, but I cannot solve it. So I'm saying all the monomers are uncorrelated. So this is the first assumption. The second assumption is monomers are uncorrelated. Uncorrelated. Or independent. It's the correct word. Independent. Independent. So what it means, that's what I told you, that it's not a right picture. Because what actually the picture in my model is, this guy points to the right, this guy can point to the left, and that guy afterwards can point to the right or to the left. They are completely unrelated to each other.
Even if it causes them to not be connected?
Yeah. Okay. Well, it's always going to be. So this guy pointing to the right. The next one can be in this direction. Okay, so let's assume that first was pointing to the right. The next guy have four options. Here, 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 and here. They are always connected. So they are always connected. The direction is uncorrelated. Basically, direction here is the state. The state of this guy is unrelated to the state of that guy, or that guy, etc., etc. Okay, so how do we solve this problem now? Remember two conditions: additivity of energy and the fact that in our representation the particles have to be independent. So this is we assumed. The second condition is already assumed in the problem, so this is fine. Okay? The only thing that is left is to find the proper representation of the energy. So what is the proper representation of the energy of this system? So let's assume that this length, I call it Lx. Okay, this length I call it Lx. Okay. Now, there is a gravitational energy due to the fact that I'm pulling my weight. There is a weight here of the size mg, and I'm basically pulling it downwards. Okay, so I'm saying there is a gravitational energy, which is simply what? Which is E gravity is some E0, okay? Is some E0, which is where I actually say where is the base energy equals to 0, minus mg Lx. Okay? So of course the energy of this guy. Okay? And I want to rewrite it by the terms of tau, because it's usually tau is the tension that I'm imposing on the string. So this is E0 minus mg Lx. Tau Lx. Tau Lx. Fine?
Why times Lx and not the height of the
Because this height plus this length is constant, right? Okay, there is a specific constant length. The total, think about it, there is a specific number, important questions. The number of monomers, where we write it, over here, 3. The number of monomers is n. Right? So there is a specific given length of this part, which is basically n multiplied by the size of each monomer, which I also haven't provided to you. And this is A. Okay? So A is the length of each monomer. Then we have a maximum length of this monomer, of this polymer, which is n multiplied by A. Okay? So it has somehow enters into this base energy. Is this clear?
But when talking about mg, Lx is not the height.
Again, yes.
So why are we putting it in the energy like that?
Why do we pull? So what is the total length? So let's assume that there is a total length of the string, right? Mm-hmm. Okay. Now, what is the total length of the string? Is n multiplied by a plus something, plus a specific constant, plus c. Right? Okay? So I'm saying the following thing. This guy, okay, is Lx, okay, plus Ly. Right? So I have to put here minus Ly, minus Ly. Okay? But this is L and this is constant. Okay? So Ly equals to L minus L minus Lx. Okay? So all of this tau Ly equals to tau multiplied by L minus Lx, which is tau multiplied by L minus tau multiplied by Lx. Okay, so this is a constant. This is proportional to Lx. Lx is going to change. And I also have another constant over here. Right? So everything is represented in the following fashion. E equals to E0, this is the base, the ground base, plus L tau x minus tau multiplied by Lx. Okay. This is a constant. And anything that depends on the number of monomers that are lying in those directions is only this part. I don't care about the constant energy. I only care about the non-constant term. Okay, so let's call all of this EC. Okay, so E equals
Tau.
what?
It's supposed to be just tau, not tau x.
Tau. Okay. EC minus tau Lx. Okay. Then this is kosher? Yeah? Fine? Okay. So this is EG, EG. And this is fine. Okay. So this is E gravitational. What else do we have? What else do we have? We have additional energy. Energy due to excitations. What are the excitations? Remember, so there are some particles that can be in a state that they are going up or they are going down. This is the excitation. The minimum energy for each monomer when it lies in the direction of the force or in the opposite direction of the force. Right? Now, there are also some monomers that somehow, because everything here is stochastic, probability, somehow they decide to lie in the direction which is perpendicular to the force. So they have energy E epsilon. Okay? So this is the additional energy due to excitation. So let's call it E epsilon or EE equals to, we have the number of guys that lie in the Y direction plus the number of monomers that lie in the minus Y direction multiplied by epsilon. So this is my total energy, right? I have a gravitational energy and I have an excitation energy. Do I have any additional energies in my system? No? Are you sure? Do I have any additional energies? Can you shake hand? No, there is no additional terms of my energy. So E total equals to EG plus E excitations. Right? So E total equals to EC, which is a constant, remember it is a constant, minus tau multiplied by Lx plus Ny plus N minus Y multiplied by epsilon. Okay, so this is my total energy. Now, I don't care about constant parts. This guy is constant. Energy is always defined up to some constant. So let's throw it away, right? It's not important. So my energy eventually is minus tau Lx plus N Y plus N minus Y multiplied by epsilon. Very good. But not so good. Why it's not so good? Why it's not exactly so good?
You don't know what Elix
is. It's not the reason, it's part of the reason. What is the goal of my dancing over here and trying to plot the energy? Why I'm doing this?
To use the microcanonical example.
Sorry, say it
In
again?
order to use the microcanonical example.
Not microcanonical example. Two specific conditions. Factorizations, and we have here, what else? Additivity. I want to represent this energy. This is the total energy. The first condition in my prescription of solving problems in statistical physics is to write the energy as a sum of energies of different particles. Okay? This is what I want. This is what why I was trying to represent everything here and write the total energy of the system. Okay? This is my goal. Is this a sum of energies of different particles?
No.
Not exactly. Okay? And we will. So what we need to do is to represent this as a sum of energies of different particles. Okay? Now, what is Lx? First of all, what is Lx? Lx is nx minus n minus x multiplied by a, right? So this is the total number of monomers that are pointing from left to right minus the total number of pointing that pointing from right to left multiplied by the size of each monomer. Right? So this is the total size. Okay?
It isn't supposed to be plus because it doesn't really matter if the arrow is pointing left or right.
So no, this is the total length.
Yeah, but it doesn't matter if the arrow is pointing this way or this way. It counts in the length.
The total length? No, they're going to cancel each other. So if I have an arrow pointing this direction, and I have only two monomers. One is pointing from left to right, and the other one from right to left. What is the total difference of this polymer? 0, right? So this is why nx minus n minus x. Okay, so the total energy is minus tau. Instead of Lx, we write nx hat minus n minus x hat A plus ny plus n minus y multiplied by epsilon. Now remember, my particles have the following energies. 0, 0, epsilon, and epsilon. Okay. This is not exactly a sum over all the different particles. So this is a sum, right, on all the excitations. This is a sum on all the excitations. But let's look on this guy and we say, okay, so what do we have over here? We have tau multiplied by the total number of particles that are pointing to the right multiplied by A. Okay, so if we not only look on a single particle, okay, we're looking on its energies and we say we defined it like 0 epsilon 0 epsilon. But if we add to this particle a little bit different representation, so not our original particles but new particles that will look like this. I want to represent this. So this is already a sum. This guy, it's already a sum over all particles that are pointing either upwards or downwards. Right? This is the sum. Now I also want to represent this as a part of the same sum. So I'm saying if the particle is pointing from left to right, right? So it's not contributing to this part, okay? But it can contribute to this part, right? If it's pointing from 0 from left to right, it's contributing as much. How much is the contribution of this particle? Is tau multiplied by A multiplied by minus. So this is minus tau A. Instead of 0, I'm giving any particle that's pointing from left to right, I'm giving it an energy. Okay, what's happening if my particle is pointing not to the right, not to the left, not upwards, not downwards, it's pointing to the left. Where is the contribution? Over here, right? So instead of 0, I will give it tau A. Okay. So now, okay, I'm looking on this, I'm saying this is a sum over all particles, but those are new particles. And for those new particles, we have 4 states, but different energies. So the energies to go up or go down, to be in state up or state down, is exactly the same as previously. But the position, or to be positioned, to be in a state that points to the right, the energy is going to be minus tau A. And to be pointing to the left is going to be tau A. Now this is intuitive physically. Why it's intuitive physically? Remember what I said to you, excitation, I have to pay energy, right? I have to pay energy if I'm not pointing in the direction of the force. So this is epsilon, and epsilon. Great. Now, what happens if I'm pointing in the opposite direction of the force? I also have to pay some energy, right? It's not preferable. If something is pulling me to the right, and I'm pointing to the left, it's not a preferable state. The system always wants to be in a minimal energy. So what we got over here, if we are pointing in the opposite direction to the force, we are paying some energy. So this is good. We have here a positive energy, tau A. If we are pointing in the direction of the force, we have to have a minimal energy. What is this minimal energy? It has a sign minus, so it's indeed minimal with respect to all the other parts.
So why didn't we assume it from the beginning?
Because it wasn't true.
But you just said that we have to pay energy in order to be in the opposite direction of the force. So why didn't...
But if I have no force, if I have no force in my system, okay? If I have no force on my system, those guys have to be 0. I described to you how the monomers behave, right? How the monomers behave on their own. When I apply a force, I need to find out what happens to the system. This is the response of the system to the application of force. Sorry? No, we do. We have. So instead of having particles that are not interacting but have only two states of four states, and there was 0, 0, epsilon, epsilon, now we have the same particles that have epsilon, epsilon, minus tau A and tau A. So the energetic levels of the particles are different. My particles are different. Right? The original particles were epsilon, epsilon, and now I have a different energetic levels. I invented new particles. Right? So what I'm doing, I'm writing this energy as what? As a sum over I goes from 1 to n of what? Of epsilon I. What is epsilon I? So epsilon I has the following four states. Okay? It has minus tau A if I'm pointing to the right. It has epsilon if I'm pointing to the up. It has tau A if I'm pointing to the left. And it has epsilon if I'm pointing downwards. Those are my different energies. All those nx, minus nx, ny, minus ny. I'm just going over all the particles I'm asking. You're pointing where? Up, to the right, down, or to the left? All those nx hat, minus nx hat, this is just the count. So instead of saying or representing them by the number of nx, I'm just saying, well, let's count all the different particles. Let's count all their energies. Okay? And it's going to be the same expression as we have over here. But this is preferable. Why is preferable?
Now we can use the canonical ensemble.
Exactly. This is additivity. So this is the first condition. Additivity. So additivity. Check. And factorization. Okay. It is equivalent here. All the particles are independent. Because those are different states. They have exactly the same energy, but this is a different state. You're right. You're right. Okay. Yes. No. So this is what I was answering before. I need the total length. It was in the EG over here. And what is the total length? Let's assume again that you have only, so the question is, why do I need this representation of Lx as nx minus n minus x? Because what happens if I have two monomers, one is pointing to the right, the other one pointing to the left? The total length of this polymer that is that have only two constituents is 0. Yeah? Sorry? No. Where? No. This is the constant part. This is the constant part of all the constraints that I had before. Okay, so you remember the total length was something and I added inside all these constants. Right? Now, we also have here, so this is number 1. This is number 2. And we also have third condition, all the particles, quote unquote, are identical. What it means? That they are identical. That the partition function of particle number 1 is exactly the same as the partition function of particle number 2, as the partition function of the particle number 3. So in order to compute the partition function of the whole system, Z equals to a multiplication from 1 till n of Zi. Now, because of the third condition that they are all identical, all the monomers are exactly the same, this is simply Z1 to the power n. So our whole question about the behavior of the system comes down to what? Comes down to computation of Z1. This is why we were dancing around. This is the only way that we know how to solve it. We need to represent everything by means of independent particles that contribute additively in an additive way to the energy. How we compute Z1? It's very easy. Right? What is this? We are simply going over all the different states of my new particles. Okay, we go from clockwise, right? We start, so it can be either in position that it points to the right. So this is e to the power minus beta minus tau a. Okay. So this is position number 1. Position number 2 plus e to the minus beta epsilon. State number 3 minus beta tau a. State number 4, the energy is epsilon plus e to the minus beta epsilon. Okay. So we have here Z1 equals to e to the power beta tau a plus e to the power minus beta tau a plus 2 e to the power minus beta epsilon. This is 2 times cosine, hyperbolic cosine, right? So this is Z1 2 cos of beta tau a plus 2 e to the power minus beta epsilon. This is Z1. If I want to compute Z, this is simply what? 2 cosine beta tau a plus e to the minus beta epsilon to the power of n. Very, very nice. Okay. So if I want to compute this free energy, where 2, thank you, minus 1 over beta log of z, and this is nice. Okay. What is an interesting quantity? So everything is done, right? The moment I have here, I'm done. And from this guy, from the free energy of Helmholtz free energy, I compute whatever I want. Whatever I want. I just need to know from the class on thermodynamics what is the correct derivative with respect to what, or how many derivatives I have to take. Now you have all this list of different Maxwell relations, etc., etc., etc. We have to take a couple of derivatives and we are done. Right? Sometimes it's not that simple, but eventually it's a technical problem now. Now, what can be an interesting question over here? Remember, so this is, let's consider this is my monomer. Of course, my monomer cannot be like this, but let's think that this is my monomer. This is tau. Right? And a question that I can ask myself is, I can measure this distance. I can measure it experimentally in a lab, right? Let's consider that this is my DNA. This is my bead. I'm pulling my bead, so I'm pulling on this DNA. And I can measure, because I can visualize my DNA, I can measure, or I can put a marker over here. Right? So I can measure the total length of my DNA. And I'm interested in a response to the force. I apply different forces over here, and I want to measure this, the elastic response of this DNA. Remember, in physics, but it's also in biology, we don't know to solve a lot of problems. So all our intuition is based on the problems that we can actually solve. Okay, so if you look on this, We say, well, maybe it's some sort of a spring. Okay, the spring has an elastic constant, but everything is, to some extent, is elastic constant. So I want to measure the elastic constant of a spring. Okay. I want to measure elastic constant of a spring. How I do it? Well, I can do this in the lab, or I can do the simplification. Right? You can do the simplification. I can compute the free energy. I can compute the free energy, and maybe then I can infer something about the different states of the system. Remember, I can perform, nowadays it's a little bit, it's not so true. I also I do have information about microscopical world. But in biology, it's still difficult. I can perform microscopical computations. I can measure the total distance of the DNA. But I don't really know how those different monomers, how exactly do they perform? Okay? How they affect each other? What they are in interstates? How I can infer those interstates from a macroscopical experiment? I can apply this force. I can measure this Lx on average. Okay? And then use this formula over here, or this formula, in order to infer what are the different epsilons. Okay? I don't know what the epsilon are. Right? This is a microscopical property that I simply put inside by hand in my model. Okay? I don't know what the hell it is. I don't know how exactly to measure it. Because it's microscopical property of single monomer. But I can perform a macroscopical measurement and then connect this Lx to this epsilon. Okay? And also maybe learn a little bit new physics about complex systems, because this is not a spring. This is a DNA, this is a polymer, this is something else. Maybe it behaves differently than a spring. For example, what happens to a spring when I heat it up? Is it easier to extract it, or yes? Well, we have an experimentalist here. I'm not. But you're actually right. I heat a spring, it becomes much less stiff. Okay? I cool it down, it stiffens. Is the polymer behaves in the same way? Okay? So this is something that we can actually now check. Okay? So what we are going to do, hopefully, is to compute this Lx over here. Okay? Look, I started from a complex system. I simplified it enough so that I can solve something. I obtained this formula over here, and now I can go backwards and say, well, is it real? Is it not real? How it behaves, etc. So a lot of actually important experimental questions can be answered by this formalism. And it's not far-fetched. In nowadays, experiments that are performed on polymers, they're using exactly this same formalisms that I have over here. Okay? You can go to a biophysical labs that actually measure forces and interactions inside the DNA, and you will see that the computation is on the same level as we have here on the board. All right, so let's compute Lx. And actually, Lx, what happens to Lx? It fluctuates as a function of time, because all the different monomers, right, what they are doing, they're in equilibrium. But it does not mean that, well, sometimes it points to the upwards, sometimes it points downward, well, upwards, downwards, to the side, to the other side. It fluctuates. So if I am looking on Lx as a function of time, okay, so you can ask any experimentalist on any quantity for a system at room temperature, or any temperature that is not close to zero, the quantities are performing some sort of fluctuations. So if this is time, and this is Lx, this guy in a microscope is going to look like this. Why? We now understand why, because all the different monomers can switch their direction to the left, to the right, down, etc., etc. So it's more complicated that we are trying to describe this, because if this monomer, if I have two monomers, if this monomer pulls upwards, this guy also want to perform some, maybe it want to also pull to point upwards or whatever. We are assuming that they are completely independent. So this is a big simplification, but it still works. Now, so Lx is stochastic quantity. We don't know anything about this stochasticity, but we can compute what? The mean value. So this is Lx average. This is something that we can compute from this guy over here. We just need to know from the class of dynamics that majority of us don't really like is what derivative to take. And I never know what derivative to take. Really. What do we do when we don't know what derivative to take? So we either look in the book or...
Right differential?
Try everything.
Sorry?
Whatever works.
Whatever works. But it's easier to sometimes to compute it from scratch. Okay, so if we don't know anything, either we look for a book. So 2 weeks ago, I was working on a problem, and in one book it was saying it was solved in that and that book. So I searched this other book for around 3 days. Eventually I found it in the math department library. Was so excited. It was an article from '64. I found this article, it was in the basement there. I opened the article, I read it, and there was nothing about the problem that was pointed out. Absolutely nothing. Right? So sometimes the solution is there and somebody has solved it. So this is easier to go in the book and look for a formula, but sometimes it's impossible, so we have to develop it ourselves. It's easier, in a lot of cases, not to go into this differentials of f, but actually ask the following question. So what do we have? What is Lx? Nx minus n minus x, right? Multiplied by a, some average number. Right? This is Lx. So what we have on the left hand side? Let's look on this as what? As Li. Okay, what is Li? Li, the length on the length or the projection on x-axis of monomer number I. So this is Li. What are values Li can take?
0, 8, 1, 1.
Not 0. Why 0? 0. But we start from. Okay. So remember, there are 4 states for each monomer. If the monomer is pointing to the right, what is the size of Li?
0.
The projection on x value, not 0. A, you are right. So we have A if it's pointing to the right. If it's pointing upwards.
0.
0, the projection of the size of the monomer, not its energy. Okay, so this is 0. When the monomer point upwards, it's perpendicular to the x-axis, so its projection is 0. When it's in this state, so this is minus A. And when it points downwards, 0. So this is our quantity, right? This is the size or the projection of my monomer on the x-axis. So what do? I want Lx average. Instead of writing it like this, yes? Suggestion? Question? Yes?
You have the probability for each state.
We do have, yes, but beforehand. What is Lx? It's my conductivity of the energy. It's a sum over I, Li. Yes? No? Okay, so Lx average is an average over a sum over I, Li. Am I right over here? Okay, average is a linear operator. So this is average of a sum is a sum over averages. So a summation over I from 1 to n of an average value of Li. Okay.
What is tau?
Okay, this is they are completely independent. Okay, so this is simply n multiplied by L1. This is Lx.
Stas?
Yes?
Can't we add a tau in front of A or
No, not energies. These are the sizes. I don't care about tau when I'm talking about the size. Size of the monomer, the projection. The probability is going to be related to tau. You're right, but the size not. Okay, so this is my equation, you see? I haven't had to perform any derivatives, just to think a little bit probabilistically about the problem over here. Why it works? Because this quantity is like energy, it's additive. And I already have a representation of my different particles. Okay? So anything that it's additive, it's simple to compute. So I need to compute this L1 over here.
You just said that we have different values of Li.
Yes.
So why do you multiply by n if you don't know?
But the average value is exactly the same for the first monomer and the second. Is there any difference between the first monomer and the second monomer? So the average values has to be exactly the same. Okay? Great. This is the last step. What is L1? L1 average is the probability of the b to the forward multiplied by the state when the particle is forward is A, plus the probability of to be in the upward state multiplied by 0, plus the probability of being in the left hand state multiplied by minus A, and the probability to be in the down state multiplied by 0. Okay? So L1 average equals to, what is the probability to be in the up state?
use the canonical ensemble.
Exactly, the canonical ensemble. This is why we developed this stuff. Okay, so this is e to the power of beta tau A, the probability to be in the upward state, divided by Z1 multiplied by A. This is 0, I don't care. So I have minus A e to the minus beta tau A divided by Z1. Okay. So in total, I obtain that L1 average is A. So this is good. Units of length. A is length. Multiplied by 2 hyperbolic sinus of beta tau A divided by, what was my Z1?
Cosine?
2 cosine hyperbolic of beta tau A, right? Plus 2, plus or minus? Plus e to the minus beta epsilon. Okay, so Lx, my total length, equals to n times A times hyperbolic sine of beta tau A divided by 2 cos hyperbolic cosine of beta tau A. There is 2 over here. Plus 2, what?
It's multiplied by 2, not the power of
Z1.
2. No,
Z1 has 2 over here and 2 over here. It's multiplied by 2. So there are parentheses over here. Okay? So it's not a to the second power. Okay? Now we can get rid of the 2's, and this is our answer. This is our answer. So does it look like a spring? You don't think so. Neither do I. Why does not it look like a spring?
What's springy about it?
How spring should look like?
On average it's 0.
So if I wanted to see a spring, what behavior should I see? I should see a constant multiplied by tau. Right? If I have something, okay? If I have a spring and it's in equilibrium position and I apply the force, right? I do know that the total length is going to be proportional to the applied force. This is an equation for a spring. The extension is proportional to the applied force. This is the spring that we know from high school. Okay. Here we have something which is blah, right? It's not proportional to anything. Well, it's proportional to A, which is good, but everything else is blah. But this is actually not so bad. Why?
Asymptotically, sinus hyperbolic and cosine hyperbolic is 1.
Now, wait, no. No, sine is 0. So, springs exist in nature only when the applied forces are small enough. Okay, so if I have a spring and I pull it immensely, it will break down, right? It's not going to be proportional to the force. It will simply break. Why? Because all the elasticity that you have learned is breaking down. There is a non-elastic response when the forces are too strong. So all our assumptions about forces, which we call nowadays linear response, okay, this is a linear response, is applicable only when the forces are small, not big. So what I need to do is I need to take this expression over here. I need to take the expression from here and I look on the small, not temperature, look on small tau limit. So this is only when tau goes to 0. Okay? This is only when tau goes to 0. When forces are large, I do not expect linear response. But when the two forces are small, well, this is actually what happens, right? When I press on this table, it actually extends a little bit proportional to the amount of force that I put on it, imply on it. Why? Because there are somehow elastic forces inside, interatomic interactions, etc., etc. The responses are small. But if I hit the force extremely hard, okay, you heard the sound. What is the sound? The sound is propagating waves inside this table. Those are no elastic response, right? The same happens over here. If my force is large, something peculiar and not nice happens. But if I take the small extension, okay, I'm going to obtain something else. Okay, so what do? I do the following. What is hyperbolic sine beta tau A in the limit of tau goes to 0?
0.
No. 0 is bad. If it's 0, then everything is 0. So I cannot take the 0.
Maybe beta tau A?
Beta tau A. Okay. Great. What is cosine?
1.
Beta tau A. This is, tau goes to 0. This is 1. Okay. So all of this, look on this guy. Lx average is n multiplied by A multiplied by beta A multiplied by what? By tau divided by 1 plus e to the power minus beta epsilon.
So under high temperatures, it's one from the spring.
Yes?
How does this
No.
How does this correspond to high temperatures?
How it corresponds to high temperatures?
לא מדברים על בטא, מדברים על תאו.
Okay. So what is the elastic spring constant over here?
N
So let's look on this guy. So Lx average divided by NA equals to beta A divided by 1 plus e to the power minus beta epsilon multiplied by tau. My equation is L equals to, or force equals to Kx. Right? Force equals to Kx. F equals to Kx. Force is tau. X is this guy. So the spring constant K is 1 plus e to the minus beta epsilon divided by beta A. Alright, this is the spring constant. Or 1 over the spring constant.
Why are you defining my NA?
Well, I just want, first of all, want to look on unitless term, and n is not, it's not a function of beta, not function on anything. Okay, you want to put here NA, it doesn't matter. So the only thing that depends on the temperature is this guy, and the only thing that depends on epsilon is this guy. Okay. So now if I want to infer what property of my model I don't know, what microscopical properties I wanted to explore. I wanted to explore those epsilons. I wanted to explore how much it costs for a single monomer not to point in the direction of the force, but actually to be perpendicular to it. Okay. I have an expression for the spring constant. Okay. I have an expression for the spring constant. And then I can go and measure it. I can compute this this K as a function of temperature. Okay. And from exploration of this function, I will obtain the only fitting parameter that I don't have is epsilon. First of all, how this guy behave with temperature? So what do you think?
Beta is 1 over temperature.
So 1 plus, let's write it, minus epsilon divided by K Boltzmann T. Okay? Beta A. K Boltzmann T. Okay. So for small temperatures, if we have small temperatures, what we have?
Wait, what about A now?
Where is A?
On the denominator.
Divided by A. Okay, so look on this guy. When temperature is small,
the exponential growth.
we have exponential growth, right? Or exponential decay. What do we have over here? It's decaying or it's growing? So T is, so what you're saying, if T goes to zero, what is this guy? It's huge, right? And this guy is 0. So we have 1. So for small temperatures, it's growing linearly with temperature. Okay? It's growing linearly with temperature. This is what we expect. But is it going to be a monotonic growth over here? Okay, so what eventually what we will have? Something like this? Whoa. Yes or no?
The exponential is 1, it's T is very large, and then you have linear growth again?
Uh-huh. So we will have something like this. No? Yes?
Depends on temperature.
But the thing is, at some point,
This won't be okay, this equation.
sorry?
הגענו למשוואה הזאת בזה שאמרנו שטעות קטן.
Exactly. Exactly. So this is something that we developed when tau is small. But let's assume that tau is still small. So what do we have over here? The behavior that we are going to get is an interesting one. So first of all, it's not always proportional to t because of those guys over here. There are going to be some modulations. Okay? Now, so first of all, in order to explore what is this k over here, we put data points. Those are the specific measurements. We can measure it for T1 and for T2 and for T3 and for T4 and etc., 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 and for T5. Okay, we will have a specific data points. Then we will feed this parameter epsilon such that our curve, this blue line, will cross those data points. The moment it crosses those data points, we know we have only one feeding parameter, one epsilon. Okay? So by performing a measurement of a macroscopic quantity, getting out of there this spring constant, we can measure what are the microscopic energies of this monomer. Okay? It's a great thing. And we measure something big and we know something about the small parameters. This is one. Another thing is the behavior that we see over here. That the spring constant can actually decay as a function of temperature. So the system, there are specific temperatures that the system becomes what? Becomes more stiff as we heat it up. Okay? This is something that we do not expect from a spring. The spring, the more we actually heat it up, the easier it's to actually to pull it apart. Here it's something different. Why is that? So this behavior comes from additional forces which we call entropic forces. So remember, when we think about a spring, we think about just one-dimensional something that we simply push into two different sizes, and it simply extends. The more we push, the more it extends, at least in the linear response limit. As we heat it more and more, the particles are loosely connected to each other. Why it's easier to pull hot springs than cold springs? When we heat something up, the microscopic particles, like in the Einstein model, they are not really connected to each other, or they're more and more loosely connected to each other. So it's easier to pull them apart. Okay? But what happens here? Why it's different? So what happens here, it's a nice description of entropic forces. Yes?
אמרת עכשיו שאנחנו מתייחסים לזה כמו קפיטים שצמודים אחד לשני ואז אנחנו מזיזים אותם. כמו עם קפיטים. איך זה...
So, we will come to this. We will come to this. But not now. So if I have this impression of my one-dimensional system, so all these different atoms are somehow connected. This is a spring. They also connected by small springs. I heat it up. Those small spring constants are more loose, and it's easier to push those particles into two directions. T1, T1, or F1. But our spring is not a one-dimensional spring. Our spring looks like something like this, right? We allow it to go into the two-dimensional world. It's not one-dimensional masses connected by springs, right? We have a lot of different monomers. They can point out into different directions, right? They can point out into different directions, and we don't care about this. So what happens as we heat up our so-called spring? At the beginning, at the very, very low temperatures, all the different monomers, they prefer to be in their lowest state. There are no excitations because excitations call a lot of energy. Remember, the prefactor of excitation is E minus beta epsilon, or epsilon divided by K Boltzmann T. Okay, this is the probability of being in upward state and downward state. So when temperature is very, very low, The probability of being on those states are extremely low, so I'm never there. So my polymer looks like this, right? For slow temperatures. Simply looks like that. I heat it up. There are some probabilities to actually going downwards, so it's extremely stiff. Small temperature, it's extremely stiff. I cannot pull it apart, right? Because there is no way to pull. I cannot, at least in my model, I cannot disconnect those simple monomers. This is what is called linear response, because like I hit on the stable, eventually I can break it, right? I'm assuming that I'm not applying extremely large force such that I can disconnect the different monomers. Okay, so in lower temperatures, all the monomers look like this, and I cannot do this, right? There is no possibility in my model to disconnect the different monomers. I start to heat up my chain, my polymer. So what happens? This guy, if it was exactly 0 before, it's now not 0, small but not 0. What happens when this guy is not 0? Some of the polymers can actually do like this, right? They are going to be in the up direction or in the down direction. Okay. There's already non-zero probability to perform excitation. So when the polymer is excited, or some of the monomers is excited, when I start to pull, there is a possibility of pulling, right? Because when I pull eventually, those guys are going to straighten up, and I will have, again, this linear representation. So this is why when I heat up, I have excitations, and it's easy for me to perform this pulling of the monomer. If there were no excitations, there's nothing to pull. Because there are excitations, I can pull it up, and some of the particles turn the angle by 90 degrees. Okay, this is nice. So this is what's happening, but we had this T dependence. I hit it a little bit more, there are a little bit more excitations, and I can, and the spring constant becomes larger and larger. I pull it a little bit more, the spring constant becomes larger and larger. Great, but it fails because we know that we have a decrease at some point. So what happens of the decrease? At some point, those guys are too mixed up. Okay, so this is good that they are mixed up a little bit, but at some point, they are too mixed up. Okay? I allow them to penetrate in the two-dimensional world. So they actually look like a clump. They clump together. Okay? I increase my temperature even more, and they become much more clumped than they were before. Now I'm trying to pull them apart. It becomes a little bit more difficult. Right? It's like a knot. Try to pull on a knot, and it stays a knot. Okay? So at some points when there are not very small amount of excitations, but huge number of excitations, right? They're becoming more and more complicated structures, and to pull those structures apart is actually difficult. This is why we have a decrease region. Great, but then again starts to rise up, because what happens? At some point the temperature is so high that everything is completely excited. At least in the model they are completely uncorrelated, so it's again becomes easier to push them apart. This is not some specific force that actually driving the particles together. Right? It's not an official force. It's not something that I introduced inside my model and said, well, there is if I raise my temperature above this and that value, the forces are becoming stronger and they're pulling the different monomers together. No, there's nothing like that inside the model. It's only property of the entropy, of the disorder that we have inside. Okay? Because of the disorder, at some point, everything is too crumpled together, and it becomes harder than for lower temperatures to pull stuff apart. Those forces are entropic, not real. Well, real because we can measure them, but they appear due to degrees of freedom. The moment that we allow the system to penetrate into additional or to obtain additional degrees of freedom, those degrees of freedom can actually mean something valuable and interesting. Right? So our polymer is never going to behave like a usual spring. Why? Because it can be extremely crumpled. It's not one-dimensional. Okay? It's two-dimensional or three-dimensional polymer. And those additional dimensionalities, they are important. So it's not only that we can extract this quantity epsilon, we can also understand something about what happens inside the monomer. Right? So all this story that I told you about, I do not see it in a microscope. Well, now maybe I can, but 20 years ago I cannot see it exactly in the microscope. I obtain all this information by looking on the macroscopical property over here and trying to understand what caused this non-monotonic behavior. What happened in my model? Okay, so what I learned. First of all, I learned that I can extract different specific energies from a regular or complex physical system by looking on a very simple model, measuring it. I'm performing a fit between my theory and actual measurements, and it works not bad, works pretty well. B, I learned a very important lesson. Physics is not about very specific behavior, right? We basically throw out everything about polymer physics out. We kept a little bit, right? That there are excitations, and then there is a string. That's the only thing that we left inside the model. And still we got actually a very nice description of what's going on inside. It's a qualitative description, not a quantitative one. Right? I cannot exactly say what is the exact shape, etc., etc. We can leave it to the chemical physics department. Right? But we do understand from very first and simple principle of what's going on inside a system when we apply those tools of statistical physics and very simple models. So this is a way of statistical physics. Forget about complex environment, forget about all the details. Keep the crucial ones inside, look on the very simple models, and they become extremely non-simple very, very fast, and try to apply the laws that we learn now and we learn in the next lessons to those systems. So we are done to today. The plan was to tell all of this to you in 20 minutes. Took a little bit too much, but we will continue on Tuesday on something else. Thanks. כן, כן, כן.